microphone working, yeah?
Yes.
Yeah, good, thanks. Yeah. I'm starting something which is very modest. I'm not constructing any Hopfions. Even the Hopfion in 3+1 dimensional case was very difficult to construct. So the only thing I'm going to talk about is the topological invariant of the Hopfion and whether one can do something about it in higher dimensions. Obviously, well, to start with, okay, this is the outline. The topological charge density of the Hopfion is known to be the Chern-Simons density. So in higher dimensions, it will only be in odd number of dimensions that we can aspire to construct Hopfions. So I will consider in this attempt 3, 5, and 7 dimensions only. Okay. Given that its Chern-Simons density is the topological charge density, it means that we need a connection and the curvature. As such, we are restricted to complex sigma models where we can define composite connections. The composite connections of the composite curvatures will be our building blocks. And therefore, wrong. Yeah, so these connections can be either abelian or non-abelian. So in the abelian case, it will be CPN sigma models, which will be the building blocks. And in the non-abelian case, it will be the Grassmannian models in 4n by 2n Grassmannian models. And then we shall indulge in some wishful thinking and require suitable boundary conditions so that Chern-Simons density has a chance of having a integer valued volume integral up to angular normalization, of course. So here are some generalities. I can't read it as fast as you can, so I don't even know. The point is that as far as I know, there is no existence proof for the existence of Hopfions, even in 3+1 dimensions. The only thing that is mathematically established is the topological lower bound. This is the Vakulenko Kapitansky proof, and I'm not going to extend to that at all here. I'm going to restrict only to the geometry. Okay, I think I've said everything already here. Right. The most important thing, as far as I understand, and I'm a newcomer, but still, that's all I can do, is that the Chern-Simons density will qualify as a topological charge density only if it can be converted into a total divergence expression. But by construction, it is not. So the only way you can have Hopfions is after subjecting the Chern-Simons density to suitable symmetries so that you can have total divergence. This is completely different from the usual solitons where you have total divergence. The usual solitons are stabilized by Chern-Tchrakian densities, and Chern-Tchrakian densities and their descendants, they're by construction total divergence, irrespective of having to impose any symmetries. Here, you have to impose symmetries, otherwise you don't have the required topological invariant. So, in this sense, the prescription I have adopted is that after subjection of symmetry, the number of independent functions left in the system should be the same as the number of dimensions in which we are working, so that you can have a curl or antisymmetric product, which will convert into which will result in a total divergence. So I hope to show this to you gradually. Yeah, I said this already. They have to be composite connections, and this is quite okay. Let me go very quick. These are cartoons. They're not equations. Well, they are actually. I hope they're even accurate, but it doesn't matter. So abelian Chern-Simons densities, nothing to do with sigma models or anything like that, are defined like this. Yeah, there's the curvature and the connection, and the Chern-Simons density is the antisymmetric product, and then, sorry, the Chern-Tchrakian density is the antisymmetric product, and then it always results in a total divergence, and then you pick this last one or any one of the components of this omega density, and you call that the Chern-Simons density in one dimension lower. These are not total divergences, and as such, they do not, when you vary with respect to the connection field or the independent field, it does not result into trivial equation of motion. It does result in a non-trivial equation of motion, which is always this. While the Chern-Simons density was gauge variant, the equation resulting from it is very well known to be gauge invariant or covariant. I'm not saying this redundantly because I would like to present later the same items for the composite connections with the intention of talking about the Hopfions. Okay, Chern-Simons densities in the non-Abelian case. Well, there's the non-Abelian curvature. There's the Chern-Tchrakian density in for the non-Abelian case, and here is the total divergence expression, and then I will demonstrate a few examples. It is much more complicated than in the Abelian case, of course. In d equals 3, in d equals 3, it is this well-known expression. In d equals 5, it is slightly less well-known, and their equations of motion, like before, are gauge covariant, while the densities themselves were gauge variant. Already n equals 3 and higher, that means in 7 and higher odd dimensions, the Chern-Simons density has more than one definition. That's because the Chern-Tchrakian density from which it comes would themselves be defined in multiple trace formulas, depending on how many dimensions you have. So, for example, in 8 dimensions, the Chern-Tchrakian density would have one single trace definition and one double trace definition. The single trace definition results into this Chern-Simons density. The double trace one results in this one. Okay, and then these are the equations of motion for all that matters. So now let me forget about gauge fields and Chern-Tchrakian densities and Chern-Simons densities for gauge fields. Now let's go to the composite connections, which hopefully will lead to Hopfion construction. Start with the Abelian case. Here is the in the Abelian case, as I declared in advance, they will be CPN models in 2n plus 1 dimensions. This is the CPN field, yeah, and this is it's a complex conjugate. It's constrained by this well-known constraint, and there is a projection operator like that. Everything is quite a canonical sigma model, of course, very well known. Because of the constraint, this constraint is invariant under a gauge transformation like this, an Abelian gauge transformation, and then one can construct this composite connection, which itself, under this transformation, transforms like an Abelian gauge connection. And then from that one can build the covariant derivative of the CPN field and the composite curvature of the composite connection. Okay, these are covariant, both of them. And what am I saying here? Oh yeah, now we just defined the thank you. We just defined the Chern-Simons densities in these odd dimensions for the abelian case. All I do is I adopt the old gauge field formulas I had and simply replace the connections by B's and the curvature by G's. B's and G's are the composite things, and then we have the Chern-Simons density. Oh, yeah, okay. Then we have the Chern-Simons density plus. Now, when you subject these densities to variations, again, you must not obtain trivial equations of motion because they are not total divergences. So what you do is you have to add the Lagrange multiplier times the constraint. And when you do this, here you get a gauge covariant equation just like before, only whereas before it was F, 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 here you have DIZ, the last one. So formally everything goes through for composite connections as they do for Yang-Mills connections. So now we arrive at the place where we have to make a suitable ansatz to convert the Chern-Simons density to a total divergence. And the very well-known case of 3 dimensions is here. We have the most general ansatz with subject to axial symmetry. One can write it in trigonometric parameterization like that, where rho is the radius in the x1, x2 plane, and then you see the Chern-Simons density reduces to this expression, which more or less manifestly is a total divergence. Yeah, it is when you convert to when you convert to trigonometric parameterization, it becomes explicitly a total divergence. And here it is, there is the charge. And when you go to spherical coordinates, then you can actually calculate this charge subject to this requirement that the extra function alpha, because we're in 3 dimensions, we're not in 2 dimensions, there's the extra function alpha in this ansatz. The extra function alpha will have such boundary condition at infinity, an integer times pi. The f is the Skyrm profile function, it's always going from pi to 0. So then you see, you get the usual, the well-known quantity for the charge, for the Hopfion charge. And then we go to 5 dimensions, it will be CP2 now. The ansatz is exactly the same as before, a plus ib, only the function which was c before now has c1 and c2 with 2 azimuthal angles in the 2 planes, x3, x4, and x1, x2 planes. Then you calculate the determinant, then you calculate the Chern-Simons density, and again it turns out to be a determinant, only now with the 2 c functions hanging out outside. And then to make it very boring, I do it, we complete the calculation and compute the surface integral and require this, there's something more here. Require again the Skyrm profile function to be 0 at infinity, but the extra function g, you see we have more functions now, c1, c2. G is the extra trigonometric function. This one must go to theta, which is the azimuthal, so to speak, angle between rho and sigma, the 2 radii, the radius in x1, x2, the radius in x1, x2, and the radius in x3, x4 planes. So it's maybe a bit of a tall order to ask for such to be so exigent about boundary values. But only when you require this, and then the alpha as before, m pi, it will again give you 1 power of higher theta pi and an integer otherwise. So this is, to make it boring, go to 7 dimension, do the same thing. Now we have 3 azimuthal angles, phi, chi, and zeta, and 3 extra functions, and the trigonometric function coming because of it is g and h. And so let's do the same calculation, only calculate the determinant. Now calculate the density subject to symmetry. Again, it turns out to be a total divergence, only now with the prefactor C1, C2, C3, and the determinant. These comma, row, etc. mean differentiation. I should have said that before, but it's maybe obvious anyway. So then go to spherical coordinates, calculate the surface integral, and if you require, I've forgotten to write f. F goes to 0 at infinity. G and h to go to theta 1 and theta 2, and these are now the 2 angles, yeah? And alpha goes to m pi, then again you get integer value. Now I must go to the non-Abelian. I must hurry. I think I have a few minutes left. 2 or 3? 3. Okay, so then to go to non-Abelian, instead of CP1 models, we go to these Grassmannian models and go through the formalism as before. There is the projection operator, there is the constraint, which is now matrix valued, and then it is invariant under this non-Abelian transformation. Correspondingly, we can define this non-Abelian composite connection, the composite curvature, and then the covariant derivative, which are covariant, and then we adopt again the old Chern-Simons densities from the Yang-Mills case, replacing A's with B's. Here's the 3-dimensional, etc., 5 and 7. We will not go beyond 7 anyway. Calculate the equations of motion. They turned out to be covariant, as expected. Nothing new about that. They are not total divergent, so they will give non-trivial equations of motion until we apply appropriate symmetries. And now there is one surprise. If I make my ansatz with the prescription that the number of functions must be the number of residual independent functions must be the same as the number of dimensions in the coordinates, then in this case, very similar to the old ansatz, these sigmas are just sigma matrices. It will turn out that the composite curvature will be abelian. So then we go to 5 dimension, and in 5 dimension we have again, like before, C1, C2 extra function, and fortunately here the composite connection is not abelian. And the same sort of determinant comes out when one calculates the charge, but now this is the last thing I really insist on saying, is that whereas it looks formally exactly the same as, very closely the same as the abelian case, there is this completely non-trivially different prefactor. So non-Abelian difference from abelian. And then I go to 7 dimensions, but that's just formalities. So thank you.
Thank you very much. Questions, please.
Can I make a comment? In fact, Lim and Yang have proved existence of Hopfions in R3 in an infinite subset of the set of all homotopy sectors. Although they give some characterization of the subset, but it's an unknown subset.
Yeah, as far as I understand, their proof is much better than anything that there was before, but it's not on the same level as the proofs, say, for monopole or vortex, not for the Yang-Mills type things. You know, not. Still, I'd be very happy because I like Yang. I mean,
they proved it. They've proved the existence of minimizers in an infinite subset of the homotopy.
That's true.
Hopfions are not only axially symmetric, they can be anything, and still the charge is integer, and therefore there should be total divergence, presence on the
Well, this is the only way I can convert them into total divergence. If you maybe some other symmetry, but there must be some symmetry which reduces the number.
Trefoil modes, they have no symmetries whatsoever, and then
Long lecture.
The Chern-Simons density is not total divergence. That much is a fact.
true, but maybe it becomes total divergence for composite connections.
It doesn't. No, that it does not. I have checked that explicitly. In many, I'm sure about that. When you impose the constraint properly, it still is not a total divergence.
Only in actually symmetric case, you say.
Only with extra symmetries, not without. That's the message.
One more question. Well, thank you very much.